Yeah, so we did have an intro to acids and bases unit, but we haven't really talked about too much of like the hydronium ion and what that means. So typically, or a lot of the times, you will see H plus written for acids, saying that a system has a lot of H plus. That means that it's acidic. But what really happens in the system is usually that H plus ion isn't just floating around. It kind of globs onto a water molecule and makes the hydronium ion H3O plus. So as the concentration of H3O plus increases, the pH of a system decreases. It's lower. And remember, the lower numbers on the pH scale mean acidic, the higher numbers mean basic. So if we have less hydronium ion, then we're in a basic system. So we can also, through Le Chatelier's principle, predict the effect that a stress will have based on the color of the solution and the pH scale. So in this example, we have a temperature change where we have a system represented by the chemical reaction below. It's in a state of equilibrium at 5 Celsius. If temperature increases to 99 Celsius, will the pH increase, decrease, or remain the same? So looking at the reaction, we see that it is positive, or has a delta H that is positive, which means that it takes in energy. So heat is like on the reactant side. So if we add heat to the system, that means the reaction is going to proceed this way, the forward reaction. H3O plus, the hydronium ion, is located on the reactant side. So if we increase the heat, increase the number of products, that means our concentration of H3O plus is going to be higher. What does that mean in terms of pH? The pH would lower because the hydronium ion concentration is increased. The pH decreases because the system becomes more acidic. When heat's added, reaction again proceeds the endothermic way to the right in this case. You can often see this in a color change. A lot of acids and base reactions, we use something called like universal indicator or acid-base indicator that is basically a color change based on pH. So you can also see this through a color change, but you could also just measure the pH based on that prediction. So temperature can also change the pH of the system as well if hydronium ions or OH particles are part of the system. Stress can also change the temperature of a system, so it kind of works both ways for this. So here we have a system represented by a chemical equation, N2 plus 3H2 yielding 2NH3. It's in equilibrium in a cylinder at 25 Celsius. If the volume of the cylinder is increased, would the temperature increase, decrease, or remain the same while the system attempts to reestablish equilibrium? Justify your answer. So here we have a reaction and we have a delta H value that is negative, which means it releases heat. So heat is kind of on the product side. If we increase the volume, what does that mean in terms of pressure? So if we increase the volume, that means pressure is decreased. And remember when we talked about stresses, that means that the reaction is going to proceed to the side with more moles of particles gas to kind of balance out that pressure change. So which side has more particles, the reactants or the products? Looking at coefficients, the reactant side has 4 moles of gas, whereas the product side only has 2 moles. So if we increase the pressure, I would expect the reaction to proceed in the reverse direction, which would then change the delta H, okay? So going this way, heat is released. Going this way, the heat is consumed. If heat is consumed, I would expect the temperature to decrease, okay? So temperature of the system would decrease. The rate of the reverse reaction is greater than the rate of the forward reaction, again, because that pressure is decreased, the pressure is decreased. That means that the system is going to go towards the side with more gaseous particles. And the reverse reaction is endothermic because whenever we change the direction of the reaction, we change the sign of delta H. Relating your Q, your reaction quotient, to Le Chatelier's principle, We have a chemist that mixes 80% N2 and 20% O2 by moles in a vacuum and finds that the total pressure is 1 atmosphere at 25 degrees Celsius. So this is kind of before the reaction begins, it's at 1 atmosphere. The Kp value of the system is 1 times 10 to the negative 30. First, we want to find the initial partial pressure of each gas. Then we want to find the equilibrium partial pressure at 25 Celsius. And then if the temperature is increased with the new Kp value, because remember K, the constant changes with temperature, find new equilibrium concentrations. So first, to find the initial pressure of each gas, remember pressure and moles are directly related. So if we have 80% N2 and 20% O2 to start with, that means 80% of our pressure is related to N2 and 20% of our pressure is related to O2. So remember, it doesn't matter for gases and pressure what the species is. Pressure is directly related to the number of moles of something. So to find the initial pressure, we multiply by 80% for nitrogen and by 20% for oxygen. So we find the initial pressure of N2 is 0.8 atmospheres and original pressure of O2 is 0.2 atmospheres. So that calculation is pretty straightforward. Because we have no NO at the beginning, the pressure would be 0 atmospheres. For part B, we need to find the equilibrium pressures. So we're going to be using an ice table. Whenever we want to find something at equilibrium, we're probably going to be using an ice table. So we're going to plug in those initial pressures, so 0.8, 0.2, and 0. The change, we don't know the value of the change, so we are going to use X to represent that. Since nitrogen and oxygen are on the reactant side, it's going to subtract, so minus X. And NO2 is going to be a plus X. Based on coefficients, we're going to have plus 2x for NO. Because remember, the reaction is N2 plus O2 yields 2NO. At equilibrium, we can express it algebraically to be 0.8 minus x, 0.2 minus x, and then plus 2x. Then we have to go back and figure out our, basically plug and chug with equilibrium values. So we know at equilibrium, the pressure of NO2 squared over the pressure of N2 and the pressure of O2. We plug in our algebraic values for each of those systems. And remember, a Kp value was given, so we can plug that in as well and solve for x. Since our Kp value is much less than 1 times 10 to the negative 4, we can go ahead and ignore the x's that are in the denominator. So if we solve for x, we find that x is equal to 2 times 10 to the negative 16. So 2x, if we multiply this value by 2, at equilibrium, the pressure of NO should be 4 times 10 to the negative 16 atmospheres. If we have, and then because this value is so small due to sig figs, the value of N2 would be 0.8 atmospheres still, and the value of O2 would be 0.2 atmospheres still. And that's because of sig figs. So if you think about it, if you take 80 minus x, and x is equal to 2 times the negative 16, based on sig figs, we're only reporting to 2 decimal places anyway. So we're going to report it as 0.80, even though it's really probably 0.7999999, whatever. And then here we want to find the equilibrium partial pressures when our Kp value is 0.0025. Okay, so it's going to be the same process, exact same as before. Our initial pressures are still the same. The change is still the same because it's related to the stoichiometry of the problem. And at equilibrium, our values are going to be the same. Here's where things get a little bit different, okay? So here, same setup. I've set it up to the new Kp value though. But notice that this is not less than 1 times 10 to the negative 4. Based on scientific notation, it would be 2.5 times 10 to the negative 3. So that is not less than 1 times 10 to the negative 4. So what happens here, we can't ignore those x's in the denominator, so we have to use the quadratic formula, which hopefully you have used before in algebra. But the setup of the quadratic equation is the idea that 0 equals ax squared plus bx plus c. Okay, so in the quadratic formula you're about to see, this value is a, this is b, and this is c. So you kind of have to rearrange the equation to show that. So here is the quadratic formula. X is equal to negative b plus or minus the square root of b to the second minus 4ac divided by 2a. Here we can plug in our values. I showed you before what is a, what is b, and what is c. And then we can kind of plug and chug, and we're going to get two answers because at first we're going to add all of this value, and then we're going to subtract that second value. So we're going to get two answers for x. We get positive 9.7 times 10 to the negative 3, or negative 0.08. So now how do I know which one to choose? What does x mean? X is equal to, in this case, pressure or maybe concentration, depending on which K value you are finding. Concentration and pressure can't be less than 0, so we can't have a negative value for that, okay? So we're going to go with the positive value, 9.7 times 10 to the negative 3. And then we can kind of plug and chug. So for the pressure of NO, our product, it's going to be 2 times that value that we saw, so 1.9 times 10 to the negative 2. For the others, we're going to subtract that value, so we get 0.79 atmospheres. And then 0.2 minus 0.0097 is equal to 0.19. So it's a small change, but it did change compared to before. Okay, so that is our notes for 7.8 through 7.10. We have a worksheet that goes along with this that you will get started on, and let me know if you have any questions.